Hey everyone, welcome to my channel. In this video, I wanted to walk you through a problem that I came across a couple years ago in an Introduction to Probability Theory course that I took in university. The textbook that it comes from is called Introduction to Probability by Grinstead and Snell. The problem stuck with me because it takes something that can sometimes feel really abstract and hard to grasp, probability theory, and applies it to a real-world life and death decision. So without further ado, hope you enjoy the video. A small boy is lost coming down Mount Washington. The leader of the search team estimates that there's a probability P that he came down on the east side and a probability 1 minus P that he came down on the west side. He has N people in his search team who will search independently, and if the boy is on the side being searched, each member will find the boy with probability U. Determine how he should divide the N people into two groups to search the two sides of the mountain so that he will have the highest probability of finding the boy. Interesting problem, and almost too good to be true. Like, to me, when I read this, I was like, you can't use probability theory to make that kind of decision. It's so high stakes. But when I solved it, I was really amazed, and it stuck with me, so I'm gonna share with you the solution now. So I start with a diagram. There's a probability P that the kid is on the east side, and a probability 1 minus P that the kid is on the west side. How might those have been calculated in real life? Well, I like to think that maybe the leader of the search team in the winter works as a ski instructor, let's say, and let's say there's 10 ski routes, 3 on the east side, 7 on the west side. That could give you a rough proxy for P, the probability that the kid ends up being lost on this side versus that side. As for U, I'm not sure how you would assess that. It's probably a low probability, closer to 0 than it is to 1. But we'll see in the final result that the solution depends a lot on that value U. And then, as was stated, we have N people to divvy up on each side, and we're trying to figure out what's the optimal allocation of that N to maximize the probability of the kid being found, but we need to define a new variable K. K will be, let's say K is the number of people that we send to the east side, and on the west side we send N minus K people. This is all we need, and we're going to solve the problem by first defining the probability that the kid is not found. So the probability P not found is the probability P that he's on the east side times 1 minus U to the K, so not found K times, plus probability that he's on the west side times 1 minus U to the N minus K. So this is the probability that the kid is not found. It's kind of like an expectation value. Just if that helps you, you see probability coefficients, but then it's on a probability again. So I'm not sure how helpful that analogy was, but this is the key to starting the problem. Because once you have the probability that the kid is not found, you can find the probability that he is found by just saying 1 minus the probability that he's not found is the probability that he is found. So let's call that capital P, probability that he's found, and that's 1 minus P times 1 minus U to the K, minus 1 minus P, 1 minus U to the N minus K. Alright, let's take the derivative with respect to K, set it equal to 0, find the local maximum or minimum, and then we will solve for K, figure out what K is the best allocation of N people depending on P and U, such that we can maximize capital P. Derivative of the constant 0, P is also a constant. Setting this equal to 0. Okay, Now, the derivative of this exponential, a constant to the power of, like, the derivative with respect to x of a to the x, there's a rule for that, and it's right here, number 4. The derivative of a to the x is natural log of a times a to the x again. The proof for that is just setting a to the x equal to e to the natural log of a to the x, where we invoke rule number 3 here, which is the natural log of a to the something is that something times the natural log of a. So we're going to use those rules to continue reducing this equation. So we have 2 negatives, that becomes a positive. We have a common factor that we can say goodbye to. And then we'll set both sides equal to one another, rearranging a little bit. Okay. So this is where we're at. We're one step closer. I think the best next step is to take the natural log of both sides, but before we do so, I'm going to break this 1 minus u to the n minus k into 1 minus u to the n times 1 minus u to the minus k, and then I'm going to just divide both sides by 1 minus u to the minus k. And then this will become 1 minus u to the 2k. So we now have minus p, 1 minus u to the 2k equals 1 minus u, 1 minus p times 1 minus u to the n. Take the natural log of both sides. Apologies, there's no minus sign right there. The minus sign from here we got rid of because we added this to the right hand side of the equation. The minus sign here cancels with the minus sign there, so that it actually ends up being a positive number or positive set of functions equaling another positive set of functions. So now we have p times 1 minus u to the 2k equals 1 minus p to the 1 minus u to the k times 1 minus u to the k. Take the natural log of both sides. Natural log of p plus 2k natural log of 1 minus u equals the natural log of 1 minus p plus k natural log of 1 minus u. And here I invoked the same rule as before, where we have an exponent, natural log of something with an exponent. You can take the exponent and make it a coefficient. We can also use rules 1 and 2, where the natural log of a product can be turned into a sum of natural logs. And now what's next? Personally, I mean, you can go a number of routes to simplify this, doesn't really matter, but I like to just bring the p's to one side and then the k's to the other. So we'll do that. Natural log of p minus the natural log of 1 minus p is the natural log of p over 1 minus p. And then we have this equaling, oh, that's an n, my bad. I wrote it looked kind of like a k. All right. We have this natural log of this quotient plus 2k natural log of 1 minus u equaling n natural log of 1 minus u. We can divide everything by natural log of 1 minus u because u is strictly greater than 0 and less than 1. We'd have some problems if it wasn't. These will cancel. This will cancel. And this won't cancel. But now we're pretty much done, actually. So I will rearrange this a bit, and then we'll have our final answer. So k equals 1/2 times n minus natural log of p over 1 minus p over the natural log of 1 minus u. And that's the solution. So that might not actually be an integer, so you might have to take the floor function of this. But this will give you the optimal amount of people to send to the east side, with the remainder going to the west side, such that the lost person is found with the highest probability. So let's just take a look at this and see if it checks out checks out with some intuitive hurdles. Say the probability P is 1/2. That means there's an equal chance of him being on the east or west side. This term vanishes because the natural log of 1/2 over 1 minus 1/2 is the natural log of 1, which is 0. And then you would just say k equals n over 2. That makes sense. If the probability P is 1/2, then you'd want to split your search party evenly between the east and west side of the mountain. Okay, now let's say U is a really large number. So it's like 99%, meaning you send just even one person to the side of the mountain that the kid is lost on. You're going to find that kid, most likely. So let's see if that makes sense here. The natural log of 1 minus 0.99 is the natural log of a very small number. And if you remember, the natural log function looks like this. So 1 minus 0.99 is some very small number. Call it like something right here. The natural log of that value is a very large negative number. So a very large negative number in the denominator also causes that to vanish. So interestingly, if U is very large, you're just going to have k equals roughly n over 2 again. The crazy part is when U is small-ish, like 5%. If the probability of one individual finding the kid is like 5 to 10%, then this can actually create some interesting dynamics. You can actually send more people to one side than the other in a very calculated manner and have the conviction that you're going to find the kid with the highest probability based on math, which is very, very fun. So you can stop the video now. Thank you for watching. I'm going to spend the last couple minutes just proving that this is actually a local maximum, because it would be kind of silly if I did this whole problem and then in fact this is a local minimum and the probability of finding the kid is minimized at this k. But thanks for watching, and I hope you enjoyed. So we're going to want to take now the second derivative of capital P. And I know I crossed out this natural log 1 minus u, but this is actually what we're going to want to take the second derivative of. So I'll erase everything besides that real quick, and then we'll proceed. So what we just did is we found this k such that the probability of the kid being found is maximized. Now we want to see that it's actually has this concavity instead of convexity, in which case we've done the opposite of what we intended to do. So we'll take the derivative of this and see if it's less than 0, in which case we're done. Okay, so now we have a common factor of negative ln squared 1 minus u. Pull that up front. And remember we said u is strictly between 0 and 1. That means the natural log of 1 minus u is negative, but the natural log of a negative, but a negative number squared is positive, and a negative positive number is negative. So this whole thing is less than 0. And if you remember, this here is the probability that the kid is not found, which is between 0 and 1. So this whole quantity is in fact less than 0, and we found a local maximum, or a global maximum. So that's all for today. Hope you enjoyed. Bye.